Hello, fellow skeptics. This is Luther Name, and this is the fourth video in the series. In this video, what we'll do is show specific examples of the application of the general law, or at least how the application of the general law can address and possibly explain in whole or in part observations that simply don't make any sense within the framework of using Newton's point mass model. So most of this video will be a description of a whole series of slides so that you can see what the consequences are of using the general model itself. Recall that in the prior video we looked at how Newton had used his description of the gravitational interaction between two objects to come up with his law of gravity. This statement comes from his Principia Mathematica and is acknowledged by all people that this is basically how the interaction between two extended objects would occur. Newton used this as guidance to develop his point mass gravitational law. However, because he couldn't solve the actual full equation associated with this statement, he used the point mass approach, center of mass, and came up with what we now know as the inverse square law of gravity. But that's an approximation, as we showed. So what we're going to show here is the consequences of being able to find and use a general law of gravity as opposed to the point mass law. This is a graphical rendition of what he was saying, and many physicists, including several Nobel laureates, have looked at it. They don't have any problem with it. This is a fair representation of what Newton was talking about. However, he couldn't solve the problem of two spheres. He could only solve the problem of a single sphere and a point mass. And so in rendering this as a point mass, his model showed then, and using our more sophisticated methods, we show also that if one point object is a point mass, the second object can be taken as a point mass also. And what we've done is extrapolate into objects of any sizes and shapes and orientations and separations as being simply described completely by the point mass at their physical center of mass and the distance between those centers of mass. So that's all their interaction. Of course, that's what we use for the orbital angular momentum. However, if we look at a scenario, this particular scenario in more detail, I took the example of the Sun and Mercury. That's one that people have looked at. We've got good measurements on the deviation of the orbit of Mercury, what's called the advance of the perihelion, orbital perihelion, which is how the ellipse doesn't close on itself, but in fact advances ever so slightly with each orbit. So what I did was I took a look at the Sun-Mercury system, where these separation distances are given in terms of the radii of the Sun, and Mercury has a very elliptical orbit that goes from about 66 solar radii to 100 solar radii. And when I went ahead and calculated using the exact general Newtonian model and divided those results at each point with the inverse square value, I got this particular kind of a shape. So this shows that the variation is not the same across the whole orbit, but in fact has deviations that are greater than and less than the actual equivalent point mass value as calculated at that point. At this time, I can't say anything about how this small perturbation might be reflected in the advance of the perihelion of Mercury. It's not clear whether or not these actually cancel. It advances over part of the and retards over other part of it. Or it may in fact do that, and the difference between the advance and retarding is in fact what we see in terms of the difference between the classical calculations and the calculations using general relativity. But I also looked at some other what I would consider to be interesting kinds of circumstances. I took a test sphere, small sphere, and once the sphere gets to be about 1% of the larger sphere in which it's embedded, it doesn't make any difference what its size is. These are very consistent findings. The scatter is very consistent. Again, what I've done is I've rendered these distances as fractions of the total radius of the larger object, and the smaller object is embedded inside it and moves inward to the center. And these are consistent variations, very small. It's not abundantly clear what that means at this particular point, since these variations are very, very small away from the point mass model. But this shows greater granularity. And you get also some different types of appearance. For instance, if you took a shell, instead of a solid sphere, you took a sphere that was made up of a shell of some thickness. And what happens is you get the typical smooth force on the object from the sphere. And when you get to the transition, as is very well known, that if you have a hollow sphere, that an object within that hollow sphere experiences no force. With the exact inverse square law, all external forces caused by the shell cancel, and you're left with something with no force on it at all. That's not the case when you use the exact law. The exact law shows that there is a transition across the boundary from the solid material to the other, and that you still don't have a solid or a simple, smooth force on the object as it's moved to the inside of that hollow sphere. Now, I also looked at cylinders. These are cylinders whose lengths are the same as their diameters, and I put them end to end. And again, as before, I took the general model and calculated what the force and divided it by the force given by the inverse square law. In this case, you see it's quite smooth. And that's because the cylinders are analytically easy to describe. Spheres, not so much. And it's hard to say whether or not the difference between using the object as cylinders versus spheres is a result of something that's going on with the algorithms inside Mathematica. That would have to be something that would have to be worked out. But in the case of the end-to-end cylinders, the variation is very smooth, and you can see that given the exact calculation divided by the point mass value, you can see that we almost have the point mass value for end-to-end considerations, but not quite. And it becomes quite different if the cylinders are long and thin as opposed to short and squat, as shown in this particular instance. If you go, though, to the cylinders side by side, you get something different. When they're side by side, and it's the same cylinders as before, where the diameter is the same as their length, and you move them from contact out to a certain distance, you get quite a variation as they're close to one another. And then that variation smooths out, and again, as you get further away, it asymptotically approaches the point mass model itself. Where this becomes of interest is that the universal gravitational constant is calculated by taking spherical cylindrical objects in proximity to one another and moving them relative to one another at particular rates and measuring what the mutual force is between these objects. As you can see, that if you took that measured data and you tried to fit it to the inverse square law, assuming that that was a correct law, there's a lot of variation in that force, and so G would become a very imprecisely known value in order to make the inverse square model match the measured data. This would be one of the stronger indications that there is an issue, because the universal gravitational constant isn't much more accurately measured now than it was 150 years ago, and the lack of recognition that there was a more precise gravitational interaction has caused people to, they never questioned whether or not the inverse square law was correct. They just scratched their heads in puzzlement and never looked any deeper than that. However, I also took a look at something that, because the whole issue of dark matter rests on the issue of the orbits of objects in the solar disk, in the galactic disk. The galactic disk is very imprecisely known. The galaxy itself is made up of a galactic bar whose dimensions are only roughly known, and a spheroidal core, and then a disk that, well, we say it's a disk that's 2,000 light years thick. It's really very imprecise, and its dimensions are much fuzzier than that. But if you were to take a test object, again, I took something the size of the sun and embedded it in the center of the galactic disk, and I calculated the mutual forces on that object from their local distributions. In one case, it was the distribution of the disk itself, and in this case, it was just from the galactic bar, where the Earth was taken to, the sun was taken to be on the perpendicular bisector of the galactic bar. It almost is, but it's not quite. And in the next one, I'll show that there is what happens when you look at the galactic core taken as a sphere of a particular dimension. And as you can see here, from the bar provides a considerably different force on its perpendicular bisector, so that if the sun is located roughly here, we're not too far off. We're maybe 90% of what the inverse square law would provide. But if you go in towards the galactic core, you start to get considerable deviations of that force from the inverse square value. Whereas if you go out further and further, it becomes closer and closer, rendered as a equivalent to the inverse square. But this is just the galactic bar. We can separate these out, and what I did was I looked then at just what happens with the disk. Again, this is in light years from the center of the galaxy, and as you can see, again I've normalized the exact calculation with the inverse square value. Though disks are very difficult to describe with the inverse square law. Very imprecise. They're hard to work with. The exact model gives you, with unequivocally, calculations of the value without making any assumptions. And as you can see, as you get out to the galactic disk, the force on the sun would be far different than just given by the inverse square law associated with all the mass of the disk being located at the center of the disk. And as you move out further, of course, what happens is it begins to become closer to the point mass value. In order to be able to get the negative values in here, again, I took the exact value and subtracted it from 1 to find out what the deviation was of the ratio from 1. As you can see, in this particular area, it's almost as if you've got a repulsive force. And what happens is that the actual general Newtonian law accounts for the attraction of the mass on the other side of the disk. And so it acts like it's more like a washer than an actual disk with a hole in the center of it. And so this negativeness is actually only apparent because we now account for attraction that don't cancel like they do in a sphere, where in the exact inverse square law, you get total cancellation from an object inside a hollow object. You don't get that with a disk and using the exact law. And if you go further and take a look at the galactic core and you look at the mutual force on a sun-sized object, well, you can see that for all practical purposes, the force on the sun at its location would be pretty close to being given by the inverse square law. So the Kepler problem would hold for that. Unfortunate thing is that the force on the sun is vectorially modified by the force from the galactic bar and the force from the galactic disk. And so you have far from an inverse square relationship, and therefore the Kepler problem is inaccurate. And you can see why the galactic rotation of objects in the solar disk would appear to be very different from the Kepler problem. And its origin has remained elusive. The origin of the uniformity of the has remained elusive, but then we haven't had the proper model to work with. And in trying to solve that problem of the orbits in the galactic disk, we've invoked dark matter. And I don't even think we've properly calculated what the effective force on an object is, because we've only used the inverse square law. So I don't think we have any idea what the hypothesis of dark matter should really look like, nor whether we need it if we took a look at what the actual values are using the exact model for gravity. So what do we got? We've had suspicions that there may be something wrong with Newtonian gravity, but we didn't go back and revet it. We dreamed up new physics, like general relativity. And because some of the results using general relativity were close to what we needed to explain the discrepancies away from the inverse square law, we didn't look further. And we've also lacked an obvious place to start, because we have never gone, we have a tendency not to go back far enough. We start with our derived first principles, and they're not really the first principles. We have to go back further, and we don't do it. And that's a failing in academic physics. We've seen a description of the effect or impact of using Newton's general gravitational law to address certain types of problems. Are they the complete solution to these issues that we've identified, such as the universal gravitational constant, or the orbit of objects within the galaxy, and possibly others? And the answer is no, but it's a new approach. It's a valid approach because very clearly there is a more general gravitational law that we have not been aware of and we've not used. And we've also invented new physics, or postulated new physics, and haven't done very well with most of these in terms of actually showing that these new physics are valid. So now we have a new tool to be able to get to the bottom of some of these issues. So what we're going to do in subsequent videos is it will start to look at some modern physics and the consequences of not understanding or knowing that there was a generalized Newton gravitational law, and we'll address some of these modern physics. The one that comes to mind, which is probably the most prominent one, would be Einstein's general theory of relativity. And what we'll show is that not only have we blundered in terms of not understanding fully Newton's gravitational law, we'll show that there are blunders within these modern physics, and that maybe we should look back into the underpinnings of these physics the same as we've looked at the underpinnings of Newton's physics. I'm Luther Name. Stay skeptical, and be sure to leave some comments. I want to know whether or not the content of these videos is useful, and if not, what would be useful. And until we talk again,